So we're going to look at the wave number in this section. The wave number is going to tell us where on that spectrum the absorption band is going to occur. We can think of our two molecules as being connected by a bond, which is represented here as a spring. And we can apply Hooke's law. If you've taken physics, you've probably encountered Hooke's law. But we're going to use it to explain our absorptions. So the wave number associated with bond stretching is dependent upon the bond strength, which is going to be this number here on the top, and the mass of the two atoms, which is going to be down here at the bottom. Now, the mass of the system appears at the bottom, so smaller atoms will vibrate at higher frequencies. We will expect to find smaller molecules on the left side of our spectrum. Bond strength is in the numerator, so we expect stronger bonds to vibrate at higher frequencies. So we expect those to also be on the left side. And that boils down to this diagram right here. Anything, X, bonded to hydrogen is going to appear between 2700 and 4000. We'll have our triple bonds between 22,000 and 23,000, and our double bonds between 16 and 18,000. Single bonds will appear below 16,000, and as you'll see, they're going to look kind of messy. That the bottom part of the right part will look kind of messy. We divide our spectrum into two major regions. We divide it into the functional group region, which is 15 and up. Between the 15 and the 4000 is the functional group, and the fingerprint region is down here. Now, the nice thing about the fingerprint region is that you don't need to worry about it too much. It's kind of messy. These are the single bonds, and there are a lot of them, and they're vibrating and they're waggling and lots of different motions. We can look at these two absorption spectra. These are both pentanols. This is 2 pentanol up here and 3 pentanol down here. You'll see that the functional groups are very similar. This is the hydroxy group, and this is the carbon that's sp3 hybridized attached to hydrogen. That's this one and this. And both of these compounds have that, and so they both look very similar. They differ in the fingerprint region, and you can use the fingerprint region for identification. There is information in the fingerprint region, but we're not going to be utilizing it because it's a little messy. It's hard to read. They do use computers, and they can gain quite a bit of, professionals can gain quite a bit of information from the fingerprint region, but we can't. So let's look at detecting double and triple bonds. I've kind of already mentioned this a little bit. We're talking now about a hydrogen that's bound to a carbon. It's this bond right here that we're talking about. The carbon can vary. If it's an alkane, the carbon will be an sp3 hybridized. If it's an alkene, it'll be sp2 hybridized, and if it's an alkyne, it'll be sp hybridized. So if we have a hydrogen that's bound to this carbon, it will absorb on the right side of 3000. If we have a hydrogen that's bound to a carbon that's sp2, it'll be on the left side of the 2000. And if we have a hydrogen that's bound to an sp, it will be even farther downstream. This is because an sp holds the hydrogen more tightly. We've talked about how an sp hybridization has more S characteristics to it, and so it holds onto it more tightly, and it causes it to need more energy to vibrate. So let's look at this in some examples. So here we have this molecule. It has no double bonds, so all we have is carbons attached to sp3, and that's what we see here. I've marked the 3000 right there. These two peaks are below that 3000. If we look at the next molecule here, we've introduced a double bond here, and now we have a peak that wasn't in the diagram below, in the absorption spectrum above. We have this new peak here. And you'll notice that it is just to the left of the 3000. I've marked the 3000 here. And it's from having that double bond. Now, if we have an aromatic, we've got a whole lot of mess going on here. This is the carbon bound to hydrogen, and some of them are sp2 and some are sp3, and so we get a broad peak, and some of it is below 3000 and some of it is above 3000. If we introduce a triple bond, you'll also notice that I'm ignoring this. In general, you will not need to use any of the peaks below, certainly below 14, maybe below 15. Okay, so here's a hexane. So this is make sure I get 1, 2, 3, 4, 5, 6. And so we get this peak here. I kind of messed it up. Is our carbon sp hydrogen. And this peak, let's get a different color. Draw. How about green? I like green. This peak is our sp3. And I know that because it's just to the right of 3000. So this is our little summary. An alkane has sp3 hybridization. Its bond is the longest and the weakest. The frequency will be below 3000. An alkene is sp2 hybridized, and its frequency will be absorbed just above 3000. An alkyne will have sp hybridization. It's the shortest and the strongest of the three bonds, and it will absorb right around 3,300. Okay, the absence of peaks at above 3,000 can mean just the absence of the carbon-hydrogen bond. So we would expect to get no signal from this molecule. There are no signal at our 3,100 because there are no hydrogens attached to the carbons here and here. And it's the same with this one. There are no hydrogens attached to these carbons, and so we don't get a signal. So you have to be careful when you look at something and say, oh, it must not have a double bond. It may be that it just doesn't have a hydrogen in the right place. So here we're going to determine whether we expect these to have a signal to the left of the 3000 mark. So we're looking to see whether they have a hydrogen attached to one of these carbons that is sp2 hybridized. And this one does. This one does not, so it will not. This one has, here's our two carbons, we have no hydrogens. This one has a hydrogen here. This one does not. And this one has a hydrogen here. And so we would expect to see, where we have a hydrogen, we expect to see that absorption. The effect of resonance on wave number. So resonance can change a double bond and effectively make it a 1.5 bond. So it's less strong. It requires less energy to vibrate. So if we have a regular ketone that doesn't have any conjugation, doesn't have any resonance forms, it will absorb at 1720. But if there's resonance, it will absorb at 1680. So let's look at some examples of this. So here we have this molecule here, and it's got a ketone. It's got this carbon attached to a double bonded to an oxygen. It absorbs at 1720. It absorbs very intensely. But when we have 2-cyclohexanone, it absorbs, this is the 7, that's 1720. So that is absorbing a little bit to the right. And that's because we've got resonance going on here. And so this bond is not as strong as a regular ketone bond was before, and so it's downshifted. If we have an amide, we will find that it's downshifted. Here is our 720, and the amide shifts it to the right. And I've got an absorbance of 1660 on that one. If we have an ester, we find that it shifts it to the left. Here's our 1720 right here, and this has been moved over, and the ester has a less single bonded character, and it moves it the other direction to 1740.